Yep, I just started recording.
Thank you so much, everyone. So today we want to talk about how you do fault-tolerant computation when you have a 2D grid of qubits. That's our focus. There are many other types of computers. We're not going to talk about that today. Just the kinds of chips that we build at Google, where you only have a qubit talking to its four nearest neighbors. Initially, the diagrams on this initial slide may seem quite foreign. The goal is to make them not foreign by the end of the talk. So let's begin. First thing first, let's start with the hardware. So what do we have? At the moment, we have a 105 qubit chip. You can see the probability of error of all the various gates in these lines, the median, the exact distribution. The summary is that we have it around a 4 by 10 to the minus 3 median CZ error probability, and that is enough to run the surface code. If you've never heard of the surface code before, just think of it as a square of qubits working together to correct their own errors. If your error rate is low enough, then as you use bigger and bigger squares, the error rate of your collective will go down. If the error rate is not low enough, the error rate of your collective will go up when you use bigger squares. So we've finally crossed that technological threshold where we've demonstrated that in principle, it's possible to build a large-scale quantum computer. We still need to make it large, make it affordable, and find a whole range of applications that make it worth doing in the first place. But the question of does nature permit quantum computing has been thoroughly answered. So this was run for 1 million rounds, stable error rates, real-time decoding, robust, more than a factor of 2 suppression of error every time you increase the code. There's no more doubt as to whether nature permits quantum computing. It does. However, this is just memory, and we want to do more than memory. We want to do computation. So when we want to do computation, first we need to characterize the errors that are left that we're going to need to deal with when we try to compute. In hardware, we get rid of most types of errors that are kind of catastrophic. So there's substantial suppression at the hardware level of cosmic ray impacts. There's substantial suppression at the hardware level of leakage errors. We don't really have an array of qubits. We have an array of multi-level systems, and it's possible for gates and other noise to excite you to higher levels. We have hardware protocols and gates that remove that leakage so that you don't need to worry about that at the software level. At the software level, we just care about two types of errors: bit flips, things that take zeros to ones and back again, and phase flips, things that take superpositions of zeros and ones and flip the sign of that superposition. That's what we need to focus on. So how do we do that? We use quantum circuits that can detect bit flips and phase flips. And again, if you're not familiar with it, just accept that this is something that can detect a bit flip. So this blue square here is capable of detecting a bit flip on the data qubits which live on the corners. So again, regardless of where you're at in your quantum computing learning journey, this represents a chip. There is a qubit on every corner. There's a qubit on every face. And the qubit on every face is being used to detect errors on the qubits on the corners. When you do this, you get information about errors. So, if there was a bit flip error right here, then we have a blue circuit, one of these ones that detects X errors. It will say, hey, there's an X error nearby. And then we can go in and locate that error in software. We never go back to the hardware and fix it. We just track the errors in software. If there was a second error, well, this one would no longer detect anything. Imagine there are two bit flip errors. The first one gets detected, flips this measurement result. The second one flips it back to where it was originally. So pairs of errors are not detectable. Instead, you would only get a signal here. This would detect strictly the endpoint of the chain of X errors. And that's really the information you get. So you do these checks, you look for phase flips, you look for bit flips everywhere. The information you get is there is an endpoint of a chain of errors here. And then you have to go back in software and work out the most likely chains of errors that explain the observed information. Track that in software, and it turns out that since as this square gets bigger, the chance of not knowing what to do is exponentially suppressed. And you can see that because we can correct any pair of errors, but if we have 3 errors in a line, you're going to only trigger, for example, this one, and that will mean you will think the most likely explanation of a signal here is that you had just 2 errors here. So more than half the diameter of the square, if that's covered in errors, you won't be able to fix it. This then feeds into the definition of a code distance. This is a distance 5 surface code, and you can tolerate up to 2 errors. Any combination of 2 errors will be tolerable, will be fixed. So, in summary, surface code works by detecting endpoints of chains of errors, and you need to have at least more than half of a chain from one boundary to the other fail, have an error, before you cannot correct the errors. Another interesting consequence of all these checks going on is that you have these logical operators. So a chain of bit flips from top to bottom is not an error in the sense that it's what we want to do. It's a logical operator. This will flip our data. So our logical 0 becomes a logical 1 and vice versa. Same here. If we apply Z operators from left to right, it doesn't trigger any, hey, there's an error nearby. This is a logical operator. It changes our underlying data. And what I really want you to take away from this slide is the idea that these logical operators must stick to boundaries of the same color. So if we have a convention of color where we have RGB, red, green, blue, is equivalent to X, Y, Z. It's an easy way to remember things. Anytime you see something red, you know it's to do with X operators. An X boundary is where an X logical operator can end. A blue boundary is where a blue logical operator, a Z logical operator, can end. So why is that useful? It means we can take pictures like this, which are at first glance quite complicated, involving a lot of detail about the low-level circuits, and reduce it all to just this 3-dimensional picture. So this 3-dimensional picture represents, initialize a bunch of physical qubits like this. Do rounds of surface code. That's the B. Here's the B. Do rounds of regular surface code, looking for errors. Extend the surface code. That's C right here. Do rounds of extended surface code. That's D right here. And so on all the way through. This 3-dimensional picture is then just a lot easier to work with than the underlying circuits. And for concrete meaning, if you have a look at these green boxes, the connectors represent this region of the picture. So this connector, this extended connector, represents just change the boundaries of my surface code. You'll notice that here we had a blue boundary, and here we've closed up that boundary. So when you look at one of these pictures, which suppress all the details of the quantum circuits, but are equivalent to a very large quantum circuit, it's important to remember that the long connectors are just boundary replacement rules. You replace final measurement of this cube and initialization of this cube with regular rounds of surface code. You replace a blue boundary here and a blue boundary here with regular surface code. So these prisms are replacement rules. They don't represent an extended patch on a physical computer. It's just the cubes that represent real space-time volume. Later, when we see bigger structures, it's just the cubes we'll be counting that chew up space-time volume. You can imagine time going from bottom to top. This horizontal plane represents our hardware, our array of qubits. And so the whole structure is then taking an amount of space-time volume. All right, so we want wherever possible to suppress the low-level details and just focus on this idea that our logical X operators, X is red, stick to red boundaries and can be dragged through structures, and our logical Z operators, blue operators, stick to blue boundaries and can be dragged through these structures. So let's try to suppress even more details. All right, so we have 3-dimensional structures, but now let's develop a graph notation that is is exactly this, but just even easier to draw. So we're going to call this a blue node. Why? Because it has two disjoint patches of blue on the front and the back. And we can just represent that as a single blue dot with the four limbs. We can also represent this as a red node. So this has two disjoint patches of red, front and back, and the four limbs. The key things that you can then note is that if you have a blue node and want to know what happens when you put in a blue logical operator, a Z logical operator, if you look at these walls, well, you can drag that line like a piece of string that is stuck to blue. You can drag it straight through. You could drag it through and turn a corner and go up. You could drag it through and come down. Meaning if and we'll upgrade our language, correlation surface, so a logical operator dragged through space and time traces out a correlation surface. If your correlation surface is the same color as the node, it must touch an even number of edges. If your correlation surface is the opposite color of the node, now let's imagine a red logical operator, propagate through, it hits this junction, it has to go in all directions. And so it fills the space. It goes in all directions. If it's the opposite color, it goes everywhere. Same color, just an even number of edges. And that's what you need to remember in terms of rules. We want to reduce our quantum circuits to three-dimensional structures, to graphs, to make it very simple to understand how our logical operators propagate through these structures. We'll alternate between the two, but let's try to get familiar. All right, so let's take a little break and go back to things that hopefully are much more familiar. This is the usual way we talk about quantum gates. A circuit diagram, something that acts on a state produces a new state as output. So Hadamard takes a zero state, makes a plus state. Controlled not flips the target if the control is 1. Truth table, very simple to express like that. But this is not the picture of gates that we're going to use in this talk. Another way that you might be familiar with is you represent your gates as matrices. So now we have column vectors for our states and matrices for the action on that column vector. And again, this is not the picture that we're going to use today. What we instead do is, well, by all means, start by thinking of the gate as a matrix, but what we want to know is how does that gate map logical operators? So here is a logical operator. Here I've added an identity gate in the form of two C0 gates. They cancel each other out. And then I've worked out what these three matrices together make, and that is two X's, or an X pushed through a C0 gate on the control goes to both outputs. An X pushed through the target goes straight through. Z on the control goes straight through. Z on the target goes to both outputs. So these four relationships are an equivalent definition of what C0 is. If you have a structure that does those four things, you know you have a C0 gate. And this is the picture that we will find is much more useful. Not a map of states, not a matrix, but a map of operators. It's equivalent and more suited to our purposes. An X going through a Hadamard gate becomes a Z, and vice versa. So those are the two kinds of gates that we're going to focus on initially and talk about in a bit more detail. So let's do that. Let's try to build a structure that realizes a controlled NOT gate. We need to show these four relationships. X on the control goes to both, Z on the control goes straight through, X on the target goes straight through, Z on the control goes to both. Let's show that. So here is X on the control, and you can trace it through the structure. You can see that it hits a blue node. I've peeled off the blue face so you can see the red correlation surface inside, but you can see how it must stick to all the red walls and must go in all directions, whereas here we have a choice and we can go down. This is a realization of logical X on control goes to logical X on both outputs. That's the first relationship. Logical Z on control goes straight through. There's a blue wall at the front, goes straight through. Logical X on target, straight through. Logical Z on target has to go in all directions here. And again, I've stripped off the front blue wall, but you can see that this blue correlation surface must stick to this blue surface, must go down here and out. And we have shown the four mappings of logical operators we need to prove that this structure implements a logical C0 gate. Now, let's go back, and as a reminder, this is not something very abstract. This three-dimensional structure can be sliced layer by layer by layer and turned into a very concrete quantum circuit. And the TQEC tool we're talking about today, it does that for you. So you can build this structure in SketchUp, export it into the TQEC tool, and the TQEC tool will build all of the low-level circuits for you. You choose the code distance, it will build the circuits. All right, here are some more low-level circuits. So we want to expand beyond just the pieces that can be used to build a CNOT gate. This is a piece that can be used to make a Hadamard gate. Now, conceptually, a Hadamard gate is very simple. You can just Hadamard the underlying data qubits. It will have the effect that your logical Z becomes logical X and vice versa. That is the action of a Hadamard gate. It also rotates the qubit, but that's a side effect we're happy to live with. You can do a Hadamard in space as well. You use a column of mixed type checks, and those mixed type checks have the effect that when you sweep a logical operator through them, that logical operator changes type. So very similarly to Hadamard gates in time, this mixed type column of checks will do the same job, and it gives us the ability to implement logical Hadamard in space. So let's look at some rules using the pieces that we have so far. So these ones we've already talked about, reducing the three-dimensional structures to different colors of nodes, same color straight through, opposite color everywhere. Hadamard will represent as a yellow box on an edge. And there's a couple of rules that we want to talk about. The first being the Hadamard rule that if you toggle the presence of Hadamard on every edge around a node and toggle the color of the node, you have done something that leaves the computation unchanged. You can imagine that over here, right? Imagine I have a blue correlation surface coming in, but it hits a Hadamard, and now it becomes a red correlation surface. But I've toggled the color of this. It's now red. Well, just as before, I have a red correlation surface going into a red node. It can go straight through, hit the next Hadamard, and come out blue again. So this doesn't change the effect of correlation surfaces from the view of the outputs. If we look at a global level, you can make this local change and it doesn't change how the graph operates on the logical operators. It means you can do it whenever you want. Similarly, we can deform this structure topologically and it will still do the same computation. In particular, I can take this chimney up the top here and I can drag it to the right. I am at all times going to have the same colors in touch with one another, so it's topologically equivalent. And in particular, it means I can drag this structure into this structure and vice versa. So whenever you have same color nodes connected, you can merge them together, or if you want to split a single node into two nodes, for example, if I wanted this four-way junction to be two three-way junctions, I could take the single node and I could split it into two, and that's allowed. Right? It leads to the same computation. All right, so let's relook at CNOT now as just nodes in a graph. If we look at it this way, well, the control node is a blue node. And reminder, what is a blue node? It's a structure which has exactly two surfaces of that color, front and back. Red, by contrast, has 1, 2, 3 surfaces of that color. So this is not a red node, it's a blue node. Similarly, over here, this is a red node because it has front and back red, whereas blue there is 1, 2, and on the right is 3. So this is a red node. So a CNOT gate is a particular type of graph where the control is a blue node and the target is a red node. And when you start thinking about that way, you can then recognize that this is also a CNOT gate. So this is still a blue node, this is still a red node. This smaller compact structure implements CNOT just as well. A lot of people ask me when it comes to fault tolerance, what is the overhead of a logical CNOT gate? And I always say, look, hang on, that's just not the right question. And right now you might be thinking, yeah, that's because CNOT can take different shapes. But the answer goes a lot deeper than that. So stay tuned and you'll see why asking about single CNOTs is really, really not the right question. All right, Here's a control Z gate, similar idea. Control and target are both blue. This is a symmetric gate, and there's a Hadamard connector in the middle. And again, provided you realize the graph, and you should try to do it with the minimum possible overhead, you have that gate. And really emphasize here, you are not in any level trading anything when you make it smaller. When it's smaller, you need fewer qubits, less time, and because you've used fewer qubits and less time, it will also be more reliable. So in every way, you want to get the smallest possible space-time volume to realize a computation. Very important. Next, let's compile an algorithm. So this, if you care, is preparation of logical zero in the Steane code. So we're concatenating a Steane code with a surface code. If that doesn't make sense, it's just a quantum circuit made out of pieces that we can now build. And we're going to build them one by one, nice and clear. So the first thing we're going to do is take all the initializations to zero and realize them using these pieces. You can do this too. So I'll share these slides with you. You can download SketchUp. You can download the template. You can follow along and build your own version of this, or build a different version of it and see if you can do it better. Highly encourage it. But let's start. So logical zero initialization, this is initializing qubits to an eigenstate of Z, blue. That's this phase. So this represents logical zero if time goes this way. So I've chosen time to go that way. You can choose it to go in any direction you wish. I chose it to go this way. Next, we want to add a little bit of memory to all of those qubits and a Hadamard gate to this one. So this is the connector we talked about before, which interchanges X and Z logical operators. Next to C naught. C naught, if you remember, is control a blue node, target a red node, and then any path of spaghetti between them that fits. So this is a C naught gate. Here is a second C naught gate. And now you can start to play some games. I can reverse this C naught gate. Still a perfectly valid C naught gate. Then I can also look in here and say, oh, all of these surfaces are red, right? The surface here is red, here is red. Well, I can squish them together. And I can flip that arm out the other way. And now I have a single control multi-target C naught gate. And by now you might be saying, aha, now I understand why you didn't want to give me the overhead of a single C naught gate, because you can merge them together. Well, just wait, it goes a lot further than that. So by pattern matching, we can do a single control 4-target C naught gate, same structure. We can add in the Hadamard, add in the measurement, but now we can apply this Hadamard rule that we talked about. If we toggle the presence of Hadamard here and flip the color of this node, I get an equivalent graph, this one. And then I can see that this whole structure here is topologically trivial. I can push it in. Anything that's topologically trivial, I want to make the volume smaller. So I just push it in. And then this elephant trunk is also topologically trivial. I can push that in. And then there's no reason to bend that comb over. I can straighten it up. And I can also then push all of these unnecessary identities in. And now what we have is a generic structure, a comb, that implements this circuit. Initialization Hadamard controlled knots, Hadamard measure. And we're about to do another one of them. We're just targeting different qubits, so we just go straight and introduce a comb that does that. And then a comb for the next one. And then we go and optimize this, because we're not close to done. We can push in those identities. We can fold down, and let's pause on that one. We can fold this comb down and push it in. And then we can take this entire structure here and curve it over the top. So that's two things that we've done to go from here to here. This is still the same computation. And then since it's all red in here, I can squish it down. And then I can keep manipulating it. Provided I preserve the topology of this structure, it's going to do the same thing. It's going to produce the same answer. So we can move this up. And then we can shorten these outputs. There's no reason for them to be long. And we can also do things like move outputs around. So it's topologically the same if this was pointing up or if it was over here. We can drag our outputs around as suits our needs. So here I just chose to move it up here. This whole structure is deformable. right? If I need to fit it in a slightly different place, it's like a bunch of Play-Doh. I can just squish it around, just preserve the topology. It'll do the same thing. It doesn't actually matter which way I run time through this structure. Whichever way you run it, the outputs will still have the same answer. The current space-time volume you get from just counting the number of cubes. In this particular case, there are 16 cubes, so it has a space-time volume of 16. And again, I encourage you to download SketchUp, download the template, and build your own version of this and see if you can make it smaller. Make different choices, do different things, see if you can make it smaller. We're going to do that right now, actually. We're going to compile the algorithm again, not, however, in the same way. Previously, we went straight to SketchUp. This time, we're going to go to the ZX graph straight away. So we take this circuit and we use these rules. So in particular, if I want to initialize something to logical 0, this is going to be a red node. We know what controlled knot looks like. We know what Hadamard looks like. The reverse of this, another red node, is measurement. And so we can just directly translate everything. Here is the graph version, the ZX graph version of that same circuit. And then we can use rules, the spider rule, merging nodes of the same color, and the Hadamard rule, toggling Hadamard and the node color to simplify it. So let's start with the Hadamard rule. We removed the Hadamard gates here and toggled the color of the node. Then the spider rule, let's merge all of these nodes up the top. Then another application of the spider rule, let's merge all of these red nodes on each line. And now we can have a look at the definition of node color again. So blue at the front, blue at the back. 2 pieces of blue is a blue node. 2 pieces of red is a red node. But what really is this? It has 2 red faces and it has 2 blue faces. So I could call this cube a red node. I could call it a blue node. Or I could call it neither. And neither is the best thing to call it. This is part of an edge. This does not deserve to be called a colored node. So if I go and look here, you'll find that I have a red node along a single path. This doesn't deserve to be called a red node. I might as well delete it, and then I can take this enormously long path and make it a nice little short one out the top, like this. This is the same computation. And then I can take these enormously long paths out to the right and make them go out the left. And then I can just rearrange the remainder so it's a bit easier to see. And we're still not done because there are more tricks. Here's a trick you can do in ZX graphs. Why can you do this? Well, let's have a look at this structure on the left and let's put in a red correlation surface here. Now, I've included the rules again down here just to remind you. Same color, even number of edges, different color, every. So if red comes in from the left, it hits this, different color, every. It's going to go out both of these. It'll hit this, same color, straight through. It'll come down here, red, hits red, same color, straight through. So red on the top left becomes red on both on the right. Well, let's look at this on the right. Red on the top left hits this, same color, straight through, hits this, opposite color, every. It highlights these 2 on the right. So even though these 2 graphs look quite different, they have exactly the same effect on input and output correlation surfaces. They can therefore be interchanged. When you see an hourglass, you can replace it with this. And we have an hourglass. It's right here. So let's isolate it and use this rule and see if that leads to a better compilation of the algorithm. So firstly, we're going to add some of these spurious colored nodes. I've extended my edge and just said, you know what? There's a red node here. So we had an example earlier of removing a particular color node. I can also add them for free. Why would I do that? Because now I can take, for example, this edge here and drag it over to that node, topologically equivalent. So let's do that. Same deal, same computation. Let's move another edge, this one, which is in the way. Let's drag that over to here. And now we've isolated the hourglass, and it's easier to apply this rule. Let's apply it. Done. So we have a different graph this time. Let's rearrange it. And now what I want to do is I want to map this graph to 3D step by step. Let's choose a node, any node. Let's choose this node. This is a blue node, so blue top and bottom. This is a blue node with 4 edges emanating from it. Let's look at its neighbors. So it has 3 neighbors. Let's add 1. And if there's any questions, just let me know. Feel free to shout out anytime. So we've added 3 neighbors. Each one is a red node with 3 edges. Here's a red node with 3 edges. And then we can start adding the remaining ones. Firstly, we can add the nodes themselves, blue nodes with outputs. So I've added 3 blue nodes with outputs. And then we can add the edges that connect them. And that looks like this. So this is a different realization by a different path of exactly the same computation. This is preparing a Steane 7 logical qubit logical 0 state using the surface code underneath it. But it's more compact. This one only has 12 cubes, so that's the best one so far. And I encourage you to have another go by a different path and see if you can make it even smaller. No claim that this is optimal. All right, now, so far we've talked a bunch about theory, ZX graphs, SketchUp, theory. But this is not just a theory talk. You can run these examples and simulate them. So here is the full set of instructions to run exactly the case that we just looked at, the volume 12 compilation of the Steane logical 0 preparation. If you follow through these steps, you will start to get, after about an hour, and after you go to the assets directory from your freshly downloaded TQEC repository, graphs that look like this. So this is the same structure. This is how it's represented on the graph. You can see that we have a blue correlation surface top to bottom coming out the front here. So if you imagine blue to blue, we have a logical operator goes in, it hits this red node, it goes in all directions up and down. That's one of them. You could also imagine that there's an interesting correlation surface that curves to the left and curves to the right, and the TQEC tool will find them for you. So here's the one that curves to the right. Here's the one that curves to the left, and it will simulate them all and work out what the probability that the measurements on that surface don't give you the right parity, that there's any mistake anywhere in any of those measurements. You'll also find all of the X correlation surfaces, and it will package them up into the minimum number of simulations. So in this particular case, you can get all of the data for all of the Z correlation surfaces in one simulation, and all of the data for all of the X correlation surfaces in one additional simulation or batch of simulations. Each one of these represents many simulations, a lot of statistics, but the tool will get that for you. You just wait for it to give you the answer. So that's the current state of the art of the tool, the ability to analyze a graph, a ZX graph, with red and blue nodes. So let's now look at just a summary of that. So TQEC, you can start with a SketchUp model. It will generate all the low-level circuits for whatever code distance you wish. By default, distance 357 is a pretty good start when you analyze the performance of a structure. It really gives you all the information that you need to extrapolate to arbitrary distances. It'll find all the detectors. So all the places that we talked about right at the very beginning where these circuits will give you information about local errors, it'll work out how to do that for you. It will find all of the observables, these correlation surfaces that snake through the structure and characterize the quality of the computation. In brief, you want every single one of those correlation surfaces to not fail for you to have the computation succeed. So the logical error rate of the entire structure is the sum of all the logical error rates of all the individual correlation surfaces, observables. In the simulation software that underlies everything, STEM, correlation surfaces are called observables. So just be aware of that. Those same STEM files can be used to drive hardware. So again, this is not just a simulation framework. We have used on our chip, which is just big enough to support 4 distance 3 logical qubits, that chip's big enough to realize logical CNOT, and indeed we have used TQEC to run logical CNOT on the hardware. And as the hardware grows bigger, we'll implement things like what's on screen and bigger things yet. So what's our goal? We want to build a tool that lets us compile a full quantum algorithm to a 2D architecture. Right now, the computers we have are pretty small, so the demands in terms of what algorithms can run on them is pretty low, but we want to make sure that the tool supports everything that is needed as those computers grow. And here is sort of a summary of just how important good compilation is. If you take this circuit and just kind of apply a naive measure of how big it is, just its area, well, then it has an area of 192, the number of qubits by the number of time steps. That would be very expensive to implement. And this is really why whenever someone asks me, what is the overhead of a CNOT gate? I say it's the wrong question. Because if you look at this, this implements this. But at no point anywhere in here can you say, well, there's a CNOT gate here. That's just not how it works. It's a structure that gives you the output of the circuit. The CNOTs are gone, the initializations are gone, the measurements are gone, the Hadamards are all gone. It all got merged together into a computation. The only thing that matters is when you compile it down, what is the overhead of the computation? You're starting completely from the wrong place if you focus on what is the overhead of individual gates. You'll never get good compilation if that's your starting point. All right, so what's the future? Right now, we are working hard on getting Y-basis initialization and measurement. So what are they good for? You can use those to do S gates. They are half phase flips, half a Z flip. All right, they're represented here by these blue prisms. That's a work in progress to implement. We still are working on implementing the Hadamard gates, so we have good circuits for them, but there's work to be done to get them into the tool. There's state cultivation. So that is the latest way to get T-states into the computation. That is definitely work for the future to compile in. And, a lot more besides. We're made good progress. We have a tool that can run current hardware, but as that hardware grows, there are many, many more things that need to be added to it to run a lower overhead full quantum computation. And that's our mission, to support the hardware as it grows and enable people to just get state-of-the-art or as close as possible to state-of-the-art compilation when they try to do algorithm research. After all, without a good compiler, you don't really know what's cheap to do in an algorithm, what's expensive to do in an algorithm. It's only the compiler that will tell you that. And right now, compilers are largely absent or just very, very, very far from what can be done. And we'd like to fix that. And with that, I'll pause there and open the floor for questions.
Austin, this is really an amazing talk, and I really impressed the progress you've made in compilation this surface code structure. So I want to ask a question about what is the syntax you are actually using to describe this abstraction? Because I can imagine that it is daunting to actually implement this code in Steane. There are just so many details. So what is the language you are using?
Yeah, absolutely. So the goal is to actually provide three types of input. So there is a tool called PhysiX that we're working on interfacing with, where you will specify just the gate list. So, you will specify initializations and Hadamards and CNOTs, and that will be the input. The goal is then PhysiX will take your very natural input, compile it down to a ZX graph, and then we'll take that ZX graph and put it into the TQEC tool, and everything else is done for you. All of the low-level circuits down to STEM and simulation is done for you. That is a work in progress. Right now, what does work is you can specify a structure in SketchUp. So earlier we saw a file. So going all the way back, we saw links to download a file, this one, that looks like this. And if you use that template file to build these three-dimensional structures and use this free version. It's only on Windows, unfortunately. If you pay money, you can get an exporter on the SketchUp for Web version. It will export to a DAE file, and that can be consumed by TQEC. So this is one version of the syntax. You literally just have this set of building blocks, you build your structure, and again, you're done. The TQEC tool will consume the output, and you're done. The third way you can do it if you wish, you don't use physics, you don't use SketchUp, you download the TQEC tool, it's all written in Python, and then you have Python commands that put nodes at coordinates and connect them together. So that is the third way. For someone that doesn't want to use the high-level inputs, you can get right down and call individual Python commands to locate nodes and connectors.
Thank you so much. Thank you so much.
Yeah, thanks for hosting. Pretty interesting and pretty informative talk. And for the audience, if you have any questions, you can feel free to unmute yourself or just tap in the chat box. I do see there's a previous question in the chat box. So
what is that question?
The question is from Ivan Fogg. Why the upper figure, which I'm not sure he or she asked for which slides, but he asked for why the upper figure is Ctrl Z. Could you explain a bit more? Thanks. Well, I guess it's for examples of the C0 and CZ.
Yeah, sure. So we can actually explain this one using the Hadamard rule. So let's start with the C0 gate. So under the assumption that we're happy with the C0 gate, after all, we went through it in a bit of detail, right? That this is a C0 gate. If we start with this and then apply the Hadamard rule, you can put a Hadamard on all three of these outputs and then change the color of this node. And you may be aware of a circuit identity that C0 is the same thing as Hadamard, CZ, Hadamard. And so that's what you would see. If you use the Hadamard rule here, you'd have a blue node, Hadamard's on these three edges, and you'll have an explicit realization of Hadamard, CZ gate, Hadamard. And then you just take away those two Hadamards and leave the CZ behind, and you're left with this. So hopefully that gives you the why this is a CZ gate. Hadamard here and Hadamard here, this is a C0 gate. And this is, if you like, the result of applying the Hadamard rule to the previous structure. Let me know if that doesn't answer your question. Alrighty.
Yeah, I think he or she is fine with this answer. And there's one more question from the audience, KH. He asked, can you discuss TQEC's relations to similar compilation approach, such as active volume architecture?
Sure. So active volume doesn't go down as far when it comes down to low-level structures. So, we really start with a very small set of instructions and then really focus on squeezing it as much as possible. So I would say that the active volume approach is a good one, but we are just trying to push it even further, really breaking it down to the lowest level of assembly and squeezing it in every way possible. So this is more general and achieves a lower overhead. As you can see, we take it down as far as currently is known how to take it down in terms of volume. Any other questions?
So also Steane, I'm specifically interested in implementing T-gate in surface code structure. As we all know, there's recent progress made by QuickEC, the cultivation approach. But it seems that to verify the correctness seems very hard because that's actually a non-Clifford circuit. And what do you think your tool might help for T-gate or non-Clifford gate?
Verifying the correctness can be done on a real quantum computer. So typically when you do simulations, you don't do T-gates, you do S-gates. You replace all the T-gates with S-gates so it stays Clifford and easy to simulate. And that's a good first step. So if you look at the cultivation paper, all of the simulations are done using S-gates and they discuss the kinds of limitations that they expect from that approach. But the best thing to do if you really want to know if something works is you go and run it in hardware. And the hardware we have is big enough that you could imagine doing that. So that is the real check. Does it work on a real device? I don't expect running cultivation to be something that is easy to do in software, and it certainly cannot be better than running it on hardware. So in short, you wouldn't use this tool to verify the correctness of cultivation. You would use hardware to verify the correctness of cultivation. Once the hardware has been used to verify the correctness of cultivation, you would build the circuits for cultivation using the tool, but you wouldn't run the circuits using T-gates using the tool.
Thank you so much. That's really clear. Really clear, yeah.
Okay.
Any more questions? Oh, there's one more question from the chat box from Hyson Zhang. What are the programmatic rules to find squashable volume?
Sorry, what kind of volume? What are the rules to?
Sorry, squishable volume.
Yeah, so you have to preserve color. I mean, let me give an example of something that's not allowed. All right. If you look at this structure, we have a red surface going into a red surface here, and that's fine. But if I push this chimney to this node, I'll have a blue surface going straight into a red surface on the top here. That's not allowed. So the colors must always be continuous and you can't break them. So it does take a little bit of experience. Like, for example, are you allowed to just take this chimney here and move it all the way over here? And the answer is no, because you couldn't get it through here. So it's not continuously deformable in that case. From a graph point of view, you're not allowed to just pass one color of node through another color of node. But having said that, with experience, you can do things like, if I go back to this initial gate here, the reversal that was done between these two steps preserves the topology, right? We have a blue node connected to a red node, but it's not so easy to see how you continuously deform in SketchUp this. It feels when you're doing the edit that it's a bit more discrete. However, if you imagine this as loose floppy plasticine, you can see that this is indeed a topologically equivalent structure. So when you practice doing this, it is likely when you use SketchUp that at some point you'll make a mistake and make an edit that's not allowed. Just always keep in mind that you must preserve the topology and you can't push one color of node through another color of node. You can't have different colors meeting at a junction. So these are the fundamental rules.
Hi, Austin.
Yeah.
Thanks for the great talk. I'm Sean from UCSD. So I found this correspondence or the conversion from the quantum circuit to the 3D structure you described it very interesting, but it's also a bit abstract for me to understand. So can you help, can you provide some prerequisites or reference for me to like understand the correspondence between the circuit and the structure
For
you present?
sure,
Yeah.
for sure, for sure. It really all starts with getting comfortable with this picture. So this is measurement-based quantum computation. The original theory was developed by Robert Rausendorf. There's a nice paper with a pretty substantial theorem proving that this kind of thing is equivalent, that a CNOT gate can be looked at as something that maps operators. And so that's really the heart and soul of the technique. So Robert Rausendorf measurement-based quantum computation has theorem number 1. That's what all this page is about. Once you accept theorem 1 in measurement-based quantum computation, it's all about finding structures that map operators in a way that corresponds to the gate. So this is an example of a structure that maps operators in the right way to be a C0. And then you want to break that down to its simplest form, and that is best done using a graph and mapping our correlation surfaces using very simple rules. Same color node straight through, opposite color node every direction. And fundamentally, that's what's going on in this, right? A C0 gate is just a control blue node and a target red node, because that's what maps the operators in the right way. A logical X will come in. It should come out both outputs, and you'll see red to red hits a blue node, goes in all directions. So we get the first one straight through, and then comes through here and goes out. So once you internalize the validity of looking at gates as maps of operators, once you're okay with that, that becomes the total focus, building structures that map operators in the right way. And once you're happy with that, you come to the realization that you can deform those structures because they will still map the operators in the right way. And to abstract deformation, you draw things as graphs. So that's what we did here. Reduce the C0 gate to the graph and then just focus on what kinds of junctions we need to realize this computation. So additional recommended reading to recap: Robert Rausendorf, measurement-based quantum computation, theorem 1. Get comfortable with converting a gate to operators. Once you're comfortable with there, you're just building structures that map operators in the right way.
Yeah, thanks for the explanation. I've seen this kind of structure in your paper with Craig about magic state distillation like all the time, but I never understand. So today is a good chance for me to get the prerequisites from you. Thank you.
Yeah. I would say today is, so there's a 2018 paper on lattice surgery that I did with Craig, and the language in there is a little simpler than here. Back then, we focused very much on merging patches, splitting patches, looking at everything as a multi-body operator measurement. So you'll see the state distillation protocol in that paper expressed as layers of 8-body X stabilizer measurement. This approach is more general than that, more powerful than that, and it allows you to really think about the whole structure as just a thing that produces outputs in the right way, in the lowest possible overhead way, without trying to work out, what exactly is any given part of the computation. You step away from that. You don't need to think of this as merging a particular pair of logical operators. You think of the whole structure as just doing a computation. So yeah, the language in here you won't find in the 2018 papers, but this is the modern state-of-the-art way of thinking about lattice surgery as just something that prepares correlation surfaces by having a particular structure.
Cool. That's very interesting. Thanks. Will this come with a paper along with the GitHub
It comes with
tool?
the community, right? So this is where you go if you want to be up to date with the latest greatest on compiling for a 2D nearest neighbor architecture. So there is a review paper. So if I click on this, if we go to that community, did you see the community now? Did the screen share switch?
Yeah.
Okay, resources and recordings, and there is a review paper here. So this is a draft in progress. I add to it as the tool progresses and we work out what works best. So it's an interactive process, but you'll find a lot of the discussion in here, discussion about how to build detectors, initialization, hook errors. There's a lot in here. So there is an associated review paper. it's a work in progress. You'll see plenty of to-dos as well. But a lot of the slides that I talked about today, you'll find in the review, and it will go into even more detail. So definitely, if you want to review paper, there is a companion one to this talk, and there's a companion community where you can ask additional questions and get involved, of course, in actually building the tool itself, which is by far the best way to learn this, to get your hands into some programming on the tool.
Yeah, thanks. That's amazing.
Yeah, as of this morning, we're at 907 members. So it's a very vibrant, active community. GitHub, TQEC, we have a bunch of open issues. If you read through those issues and one of them calls out to you, get in touch with the person that is managing that issue, see if you can contribute, or just follow along and learn something as you see the code develop. Lots of people are happy to talk to you. Okay.
Yeah. I've already in the group. And thanks again for such great lecture today. And I believe it's already about time. And we'll look forward to see more progress on the TQEC2. And of course, for the audience, I'll look forward to see you in the future lectures. Yeah.
Wonderful.
Thank you so much. Have a good day.
Thank you.
Bye-bye.